The cosmos is moving toward silence, toward frozen disorder. There's a law out there, a fundamental one, that says everything decays, everything spreads out, everything forgets. That's the second law of thermodynamics. Its central measure is entropy. Arthur Eddington, the physicist, called it time's arrow, an irreversible drift from order to chaos. But then you look up. You see a universe of breathtaking structure, spiral galaxies whirling, stars igniting in nuclear furnaces, and on at least one world, life that contemplates the mystery. That's the profound contradiction, right at the heart of everything. How can a law of increasing disorder give birth to such magnificent complexity? Why doesn't the universe just fizzle out into a featureless, lukewarm soup? By the end of this, you'll understand how entropy isn't the enemy of creation. It's the hidden architect that redefines our story of cosmic evolution. We'll travel from the smooth fire of the Big Bang to the intricate machinery of a living cell, tracing the elegant paradox, the one that allowed a universe doomed to chaos to become so wonderfully complex. This tension between order and decay, what does it make you wonder about our place in it all? A glass breaks on the floor, that's it. It doesn't come back together. That moment, it's a small version of a rule, the universe's rule, the second law of thermodynamics. In the 1800s, a scientist, Rudolf Clausius, he named it. He called it entropy, and he said it clearly. In any isolated system, the total entropy always goes up. It never goes down. It's not a suggestion, it's a commandment. Built into reality, it's the physical reason time moves one way. We remember yesterday, not tomorrow, because entropy was lower yesterday. Sean Carroll, the physicist, he says entropy gives time its arrow. We're carried by it, like leaves in a current. But what is it really beyond the term? At its heart, it's about probability. Think of a new deck of cards. Right out of the box, they are in perfect order. Ace through king, hearts, diamonds, clubs, spades. That's a state of very low entropy. It's a specific, neat arrangement. Now shuffle it. What are the odds it goes back to that perfect order by chance? They are astronomically small. A shuffled deck. Cards in a random sequence, that's high entropy. There are just so many more ways for things to be messy than to be perfectly tidy. That's the essence of it. Statistical mechanics. Disorder isn't some force. It's just the most likely outcome. Everything tends toward the most probable state, the most spread out state. We see this in two ideas. Thermodynamic entropy, that's the dispersal of energy. Heat spreading from a hot stove to a cool kitchen. And informational entropy, that's the increase in randomness, like our deck of cards. They're two sides of the same coin. Take an ice cube. In a warm room, it's a pocket of order. Its water molecules are locked, a rigid, crystalline lattice, but the room is warmer. Its molecules are jostling. The ice cube doesn't stay ice. Heat flows from the room into the cube. The orderly lattice breaks apart. The solid becomes liquid, and eventually the water molecules disperse. They spread evenly through the air as vapor. The system moves from low entropy with order concentrated in the cube to high entropy, everything mixed. Uniform, this journey only goes one way. You never see a puddle on a summer day gather itself back into a perfect, frosty cube. This law seems absolute. But it gives us a puzzle, the deepest puzzle. If entropy always increases, always driving toward disorder, then the universe today should be a bland, lukewarm sea of particles. But it's not. It's structured, complex, so the only logical conclusion is staggering. The universe must have started in a state of exceptionally low entropy. It began ordered. That's the ultimate starting condition, the wound-up spring. The spring from which all of cosmic history unspools. Why was it wound so tightly in the first place? This is the echo. The cosmic microwave background, a faint, cold glow that fills all of space. It's the afterglow of the Big Bang, cooled and stretched over billions of years. And when we look at it, we see something. It's almost perfectly smooth, a uniform sea of plasma. This smoothness right here is the wound-up spring. It's the universe's initial condition of exceptionally low entropy. That sounds counterintuitive. We might think a smooth state is boring, and a lumpy, chaotic one is interesting. But in the physics of gravity, it's the opposite. A completely uniform distribution of matter and energy is a state of incredibly high order. It's the most unlikely arrangement. Think of it like this. You have 1,000,000 marbles, scatter them randomly, they form clusters and empty spaces. That's high entropy for gravity. It's a mess. But if you could place every marble at exactly the same distance from every other marble, in a perfect three-dimensional grid, that would be a miracle of precision. That is low entropy. That was our universe in its first moments, a near-perfect grid. Roger Penrose framed this with his whale curvature hypothesis. He proposed the gravitational entropy of the universe. The disorder in the curvature of spacetime was essentially zero at the Big Bang. The geometry was remarkably flat and smooth. Penrose called the Big Bang extraordinarily special. It wasn't a chaotic explosion from a singularity. It was an expansion from a state of exquisite, almost impossible uniformity. To make it concrete, in that early plasma, the density and temperature were the same everywhere to about 1 part in 100,000. That's like taking a lake the size of an ocean and having its surface be as smooth as a mirror. Not a single wave or ripple across the entire expanse. A state of profound calm, of supreme order. It's the lowest entropy starting point imaginable. And this is the critical setup. Because a perfectly smooth, uniform universe is a universe with nowhere to go but toward complexity. It has a tremendous amount of potential energy, locked in that uniformity, waiting to be released. The moment you introduce the tiniest imperfection, the slightest ripple, gravity gets to work. It's an amplifier of unevenness. Where there's a tiny bit more matter, gravity pulls a little harder, attracting even more matter. This is how galaxies, stars, and planets are born, not from chaos, but from the meticulous decay of a pristine order. So we're left with the deepest mystery. What physical mechanism, what law or condition, could have possibly set the universe in this exquisitely tuned state of low entropy to begin with? Why was the spring wound so tightly? The answer to that question doesn't just explain our past. It defines the entire creative potential of our future. That smooth plasma had a tension in it. And then gravity took over. You have this huge cloud of hydrogen gas out in the dark. It's cold, it's thin, spread out over light years. By any normal logic of things falling apart, it should just keep drifting. But it doesn't. There's a slight ripple, a tiny unevenness left over from the beginning, and that gives gravity a place to start. Where the gas is a little thicker, the pull is a bit stronger. It pulls more material in, which makes that spot denser, so the pull gets stronger. It starts to run away with itself. This whole cloud, against the general trend of everything spreading out, begins to fall inward. It fights that idea of decay. At the center, the pressure and the temperature go up and up, until suddenly nuclear fusion starts, a star lights up, a point of order in the dark. That's the paradox of gravity. It takes what is actually a high-entropy state, this smooth, even spread of matter, and it carves out these pockets of incredible, low-entropy complexity. A star is an ordered system. It has layers from the core out. Its fusion runs in a balance. Gravity is the organizer. It works against the thermodynamic push toward dispersal. But then you have to ask, how can that be? How can making a star, this thing of such tight local order, fit with the law that says entropy always has to increase? The answer is a kind of trade, a cosmic deal. It comes down to gravitational potential energy. Think of a book up on a high shelf. It has potential energy because of gravity. If it falls, that energy turns into motion, into sound, into a little heat when it lands. That energy spreads into the room. Entropy goes up. The same thing works in space. In that big, diffuse gas cloud, every particle has a huge amount of gravitational potential energy relative to every other. They're all on a very high shelf. As the cloud collapses, that enormous store of potential energy gets converted. It becomes the motion of particles' heat. It becomes the light of the new star. And that heat and light radiate out into the empty cold of space. The entropy increase from spreading all that energy out is massive. It's far, far bigger than the entropy decrease from putting together one neat star. The universe pays for local order with a much larger amount of global disorder. That's the loophole. Structure can form, but only by making the total entropy of the cosmos even higher. This process has a name: the gene's instability. It's the mathematical point where a cloud's own gravity beats its internal pressure, and collapse becomes inevitable. And it works in steps. The biggest ripples from the early universe collapse first, making vast halos of dark matter. Inside those halos, smaller gas clouds form and collapse and ignite, the first galaxies. Inside galaxies, smaller nebulae collapse to make stars. It's a cascade. Each step is powered by gravity turning potential energy into light and heat. And each step creates new pockets of order while it scatters entropy out into the void. We see the finished product in our own solar system. It didn't start with planets. It started with a huge, spinning disk of gas and dust around the young sun. In that disk, tiny dust grains bumped into each other and stuck. Then pebbles, then rocks, then planetesimals. Gravity took over again, gathering material into the protoplanets that became Earth, Mars, Jupiter. The disk was a smooth, high-entropy distribution. The solar system we have now, with its orbiting planets and layered worlds and moons, is a system of much lower entropy. It's complex. The cosmologist Martin Rees once said gravity is the ultimate sculptor. It arranges the large structure of everything, from galaxy clusters down to a moon orbiting its planet. So you wonder, without this strange, attractive force, without gravity's power to make order from uniformity, what would the universe be? It would probably stay that featureless, high-entropy fog. A lukewarm sea of particles, perfectly mixed and perfectly dull. Gravity did the first and most basic act of cosmic creation from chaos. It built the stages, the galaxies and stars, where everything else could happen. But building a stage is one thing. Filling it with actors, with chemistry, with the chance for life, that needs a different kind of magic. One that works on a much smaller scale. A star is this seething, dynamic contradiction. Gravity pulls inward, trying to crush it, but that pressure ignites fusion, this fierce outward push. These two forces are locked in a stalemate. A temporary one, a beautiful one, and this is the critical principle. Complexity doesn't arise in calm systems. It blooms in systems kept far from equilibrium. By a constant flow of energy. A star, a planet, a cell, none of them are closed off. They are open. They take energy in, transform it, and send waste back out. Often as heat, as entropy. This constant through flow is what allows for order. Intricate order, built and maintained. To understand it, you need the idea of a dissipative structure. A concept from the chemist Ilya Prigogine. A dissipative structure is a pattern. It emerges and sustains itself because it's excellent at dissipating energy. At spreading out entropy, it's an orderly whirlpool in a river of decay. Think of a closed system, a sealed thermos of hot coffee. It will slowly cool. Reach room temperature. A dull, uniform equilibrium, maximum entropy. Nothing happens after that. It's static, but our planet is wide open, bathed in a flood of high-energy photons from the sun. That energy heats the ground, the oceans, and the Earth radiates lower energy light back out, into the cold void. This temperature difference, this constant flow, keeps the planet far from equilibrium. And within that flow, structures form. The most vivid example might be a hurricane. From space, it's a stunning spiral, a complex engine, but it isn't creating order from nothing. It's powered by the temperature difference between the warm ocean and the cooler upper atmosphere. The hurricane is a machine for exporting entropy. It takes in warm, moist air, organizes it into this furious circulation, and exports a huge amount of heat and disorder, high into the atmosphere, out into its environment. The hurricane exists because it's an efficient channel for that energy flow. Prigogine called this order through fluctuation. A small instability in a system far from equilibrium can be amplified, leading to a whole new state of organized complexity. So a star is the same principle. A dissipative structure on a cosmic scale. It takes in the gravitational energy of its own mass, transforms it via fusion into light and heat, and radiates that entropy out across the galaxy. Its fierce, stable structure is a result of that export. That non-stop export. And this brings up a question: is life the ultimate expression of this? A living organism is the most intricate dissipative structure we know. It takes in concentrated energy, sunlight or food, uses it to build and maintain its internal order, and exports waste heat and molecules back out. It's a whirlpool of chemistry, perpetually renewed by a flow. In this light, life emerging on a planet bathed in stellar energy isn't a bizarre accident. It might be the universe's most elegant trick for increasing entropy. A star builds the stage, provides the energy flow, and life, in all its complexity, may just be a beautiful way for that energy to find its path toward dispersion. A library after a storm. Books are everywhere, thrown from the shelves, pages open, spines cracked. It's a mess. To find a specific sentence in that, it's impossible. The information is still there on the pages, but it's lost. It's inaccessible. That's a state of high entropy for information. Now picture the same library but organized. Every book in its place, cataloged, cross-referenced. That's low entropy. The information is present, but it's also structured. It's retrievable, it's meaningful. This isn't just a metaphor. It points to a connection, a nexus, between the physical world of spreading heat and the abstract world of knowledge. In the middle of the 20th century, a mathematician and engineer, Claude Shannon, created information theory. He needed a way to measure information, to quantify it. And what he found, the formula he derived, was mathematically identical to the formula for thermodynamic entropy. In Shannon's framework, information is a measure of surprise, of unpredictability. A completely random string of bits, like static, carries the maximum possible information per symbol. Because you can't predict the next one, but it's also meaningless noise, real, useful information. A poem, a symphony, instructions lies in the correlation between symbols. In the patterns that are statistically surprising against a background of randomness. This is where the link becomes beautiful. A state of high physical entropy, like our scattered library, is one of many possible configurations. It's highly probable. To describe it requires very little information. You just say books are everywhere, but to describe the perfectly ordered library, you need a vast amount of information. The exact title, author, and position of every single book. That highly ordered, low-entropy state is incredibly specific. It's a configuration rich with information. In this sense, information is a form of negative entropy. It's order extracted from disorder. A complex structure in the universe, then, isn't just a physical arrangement of matter. It's a dense packet of stored information. Think of a single molecule of DNA in one of your cells. Its double helix structure encodes in the precise sequence of its chemical bases an astronomical amount of information, the entire blueprint for building and maintaining a living organism. That specific sequence is astronomically improbable. If you just toss the bases into a soup at random, the odds of them assembling into the exact sequence that makes you are effectively zero. Your DNA is a monument to information, a defiance of randomness. A spiral galaxy is the same on a cosmic scale. Its specific arrangement of hundreds of billions of stars, gas clouds, and dark matter in that pinwheel pattern. That represents a specific, information-rich state carved out of a smoother, more probable beginning. This idea leads to concepts like algorithmic information complexity, which asks, what is the shortest possible computer program that could output a given string of data? A perfectly random string has high complexity. You essentially have to write out the whole string, but a string with a simple, repeating pattern has low complexity. The universe seems to be generating structures of high algorithmic complexity. They're not random, yet they can't be described by a simple, short formula. They're complex in a deep, computational sense. Then there's Landauer's principle, a cornerstone of the physics of computation. It states that erasing a single bit of information in a computer necessarily dissipates a tiny, specific amount of heat into the environment. Logically, to reset a memory bit to zero, you have to forget its previous state. That act of forgetting, that loss of information, is an irreversible process that increases entropy. It physically links the manipulation of information to the second law of thermodynamics. Even the growth of a simple snow crystal illustrates this. As it forms, the crystal doesn't grow randomly. Its intricate, six-branched pattern encodes information about the temperature and humidity fluctuations it experienced as it fell. The crystal is a physical record, a snapshot of data from its journey. Physicist Seth Lloyd has taken this idea to its ultimate scale, proposing we view the universe itself as a giant, if slow, quantum computer. From this perspective, every interaction, every particle collision, every gravitational tug, every fusion reaction in a star is a kind of computation, a processing of information. The evolving structure of the cosmos is the output. This reframes our central paradox into a question. Is the relentless increase of cosmic entropy not just allowing complexity, but actually driving it? Is the universe computing its own fate, using the formation of galaxies, stars, planets, and life as the means to generate and process unimaginable amounts of information, all while spreading disorder out into the void? The story shifts from one of decay to one of computation. The universe has this long story, this timeline, and it's really about a trade. You start with a plasma, almost perfect. And you end up with galaxies, this huge web. That's not an accident. It's not random things coming together. It's an engine, a pump for entropy. So building all that structure, it doesn't break the second law. It's actually because of it. The universe is incredibly good at making entropy, and the way it does that is by making these pockets of order, these beautiful, complex things. It begins with the smallest differences, tiny ripples in that early plasma, variations of less than 100,000%. Those were the seeds. They made the first temperature differences. Where matter was a little denser, it was a little hotter. And that difference, that's potential, like water at the top of a hill. Then gravity starts pulling matter together into the first stars, and it converts that potential into a raging inferno. Nuclear fusion, a star is a machine. It takes gravitational order and turns it into radiant disorder. It takes a relatively smooth cloud and makes a fierce, hot point, and it radiates light out into the cold void. That radiation, those photons, that's entropy, being carried away. The process is staggeringly efficient, but the engine doesn't stop. When a massive star dies, it does it in the most spectacular way we can see. A supernova. For a moment, it outshines a whole galaxy. That's a catastrophic release of disorder. The core collapses in seconds. The outer layers blast into space at a huge fraction of light speed. The energy is almost beyond comprehension. And yet, inside that explosion, inside that ultimate act of spreading out, something happens. The heat and pressure forge elements. Things heavier than iron. Gold, silver, uranium. These complex atoms get scattered across space. So the supernova, this event of ultimate disorder, it seeds the cosmos. With the ingredients for planets, for chemistry, for life. It pays for new, richer order with an unimaginable entropy dividend. You can track this through time. At recombination, when the first atoms formed and the universe became transparent, a huge amount of entropy was released. That's the cosmic microwave background. During galaxy formation, as vast clouds collapsed, gravitational potential turned into chaotic motion, into the heat of gas. When galaxies collide, it seems violent and destructive. But they are actually driving entropy higher. mixing up stellar orbits, triggering new star formation, which then pumps out more radiation. To get the scale, look at the cosmic entropy budget. In the very beginning, the universe had astonishingly low entropy, because it was so smooth. Today, the entropy is almost incomprehensibly large, and where is most of it? The current champions aren't stars or galaxies, they're black holes. A black hole's entropy is proportional to the area of its event horizon. The supermassive black hole at the center of our galaxy, Sagittarius a star, holds more entropy in its invisible boundary than all the stars and gas and particles in the galaxy combined. Black holes are the ultimate entropy sinks. They're the end point of gravitational collapse, where matter and energy get compressed into maximum disorder, hidden from view. This whole story brings in a perspective from David Deutsch. He frames the growth of knowledge, science, technology, culture, as an entropy-lowering process. A scientific theory that explains many things, that's a compression of information. It brings order to our understanding, but this local creation of knowledge, of structure, it's only possible because we're open systems. Like stars, we consume energy and we export entropy. Our civilization runs on the same principle. We take in concentrated energy, sunlight captured by plants, fossil fuels, nuclear reactions. And we use it to build cities, encode data, explore the cosmos. And in doing that, we generate waste heat, disorder. So that leads to a question. Could we measure a civilization's advancement not by its energy use, but by its ability to create meaningful, beautiful local order while managing its entropy export? A truly advanced society might not just use energy. It might choreograph the flow, energy and information, with exquisite grace, creating islands of profound complexity without poisoning its own nest. In that light, the whole cosmic history, from the first star to the first cell to the first city, it looks like one continuous unfolding, a universe winding down from a special beginning, and finding in its own winding down the most incredible possibilities for creation. The double helix unzips inside a cell. Each strand becomes a template. New molecules lock in, one cell becomes two. That's not magic, it's thermodynamics. Life isn't an exception to the rule of decay. It's the rule's most sophisticated expression. A living thing is a pocket of order, intense, self-sustaining order, built and maintained by a trade with chaos. It imports concentrated energy, it transforms that energy, and it exports disorder back out. To be alive is to be a whirlpool in a river of energy, a pattern that persists because it's so good at spreading everything else apart. Erwin Schrödinger captured this in his 1944 book, What is Life? He said organisms sustain their order by feeding on negative entropy, negentropy. They draw order from their environment. A plant doesn't just consume sunlight, it consumes the order of that solar stream. An animal doesn't just eat food, it consumes the chemical order stored in molecules. We are consumers of order. We siphon off the universe's low-entropy resources to postpone our own decay into equilibrium. Death is when that import stops. The local structure succumbs to the tide. This process has a name, metabolism, but through the lens of entropy, metabolism shows its true function. It's not just chemical reactions for growth. It's an entropy export mechanism. An organism maintains its internal order by increasing the disorder around it. Follow the energy. Photosynthesis. A leaf captures high-energy photons from the sun. It uses that energy to take carbon dioxide and water, simple, disordered molecules, and weaves them into glucose, a highly ordered, energy-rich molecule. That seems like order creation, but the leaf pays for it. The process releases oxygen and waste heat. The total entropy of the leaf plus its environment goes up. The order is local. Purchased with global disorder, now follow that glucose. In an animal cell, cellular respiration tears it apart. Its bonds are broken in a controlled cascade. The energy released builds other molecules. It powers muscles, it fires neurons, but the process is messy. It produces carbon dioxide and water, and a significant amount of heat. Your body is a 37-degree furnace, constantly burning fuel. The warmth you radiate isn't a byproduct, it's the point, it's the exported entropy. Evidence you're maintaining your far from equilibrium state. Your body is a testament to this. Every second, trillions of reactions hum along, a symphony of controlled decay. You breathe in oxygen, a product of planetary disorder. You eat food, the captured order of plants or animals. You exhale carbon dioxide, a more disordered molecule. You radiate heat. You are a dissipative structure. You exist because you're an efficient channel, turning concentrated energy into diffuse warmth. Scientists like Jeremy England push this further. His concept is dissipative adaptation. Under the right conditions, a bath of energy, many interacting parts, matter self-organizes into shapes better at absorbing energy and dissipating it as heat. Life with replication and evolution may be the most powerful outcome of this physics. England said you start with a random clump of atoms, shine light on it long enough. It shouldn't be surprising if you get a plant. A plant is an excellent structure for absorbing sunlight and turning it into heat. So we're left with a question. A profound one. It grounds this cosmic paradox in the beat of our hearts. Are we, and every tree, every bacterium, every bird, just sophisticated patterns for dispersing energy? Are living things, in all their beauty and struggle, just elegant solutions to the universe's demand for increased entropy? If so, then our existence isn't a defiance of the trend toward disorder. It's its most intimate fulfillment. We aren't just in the universe, we are how the universe experiences its own winding down and accelerates it. That leads to a final implication. If life is a thermodynamic phenomenon, what does that say about its potential to arise anywhere the conditions are right? The Orion Nebula is a cloud of gas and dust. It glows, it's a stellar nursery, a place of beauty and violent change, and it shows the paradox. Here, the drive toward entropy doesn't create blandness. It creates new suns, it builds the elements of life. This is stellar alchemy, complexity born from decay. It starts with a cold, dark molecular cloud. Light years across, that cloud is in a state of high entropy. Its material is spread out, diffuse, but it's not perfectly smooth. There are subtle knots. Slight denser regions, inherited from the Big Bang, and gravity finds an opening there. A denser patch pulls in more gas, it contracts. Its gravitational potential energy gets converted into chaotic motion, into heat. That's the first major entropy export. The cloud fragment heats up. It begins to glow in the infrared. A protostar is born. A spinning sphere of gas drawing material from a disk. Pressure and temperature at its core climb. For a star like our Sun, this takes millions of years. Until one day, the core reaches about 10 million Kelvin. Protons are moving fast enough to overcome their repulsion. They fuse. Nuclear fusion begins. The star turns on, and a new, more powerful entropy engine starts its work. The core becomes a furnace. It takes the ordered potential of collapse and transforms it into a flood of photons, light and heat that radiate for billions of years. The star's stable structure is a result of this constant through flow, this massive export of disorder. But fusion does something else. It builds complexity from simplicity. Inside the core, hydrogen is forged into heavier elements. For stars like our Sun, this happens through the proton-proton chain. 4 hydrogen nuclei fuse into one helium nucleus. It releases energy, sunlight, and it creates a new, more complex atom. In more massive stars, a different process dominates. The carbon-nitrogen-oxygen cycle. Carbon, nitrogen, and oxygen act as catalysts. They help fuse hydrogen into helium but aren't consumed. This cycle is faster at higher temperatures. It shows a stunning fact. The presence of trace heavier elements from earlier stars can accelerate new stars. The universe is learning to build upon itself. As a star ages, its core runs out of hydrogen. For a star like ours, that's the quiet end. But for a more massive star, the end is a creative catastrophe. The core contracts, gets hotter. It begins fusing helium into carbon, then carbon into oxygen, neon, magnesium. Each new fuel burns faster. In its final days, the star becomes a layered onion. With an iron core, iron is special. Fusing iron doesn't release energy, it consumes it. So when the iron core grows too large, the supportive energy stops. Gravity wins in an instant. The core collapses in less than a second. The outer layers crash down and rebound, a supernova. The explosion outshines an entire galaxy. It's the ultimate act of entropy production, releasing more energy in weeks than the star did in its entire life. And in that fury, in the heat and neutron flux, something miraculous happens. Elements heavier than iron are forged. Gold, silver, iodine, uranium. The violent scattering seeds space with this chemical bounty. Carl Sagan captured this. He said the nitrogen in our DNA, the calcium in our teeth, the iron in our blood were all made in collapsing stars. We are star stuff, so we have to ask. Without the entropy-producing fury of stars, without their cycles of collapse, fusion, and explosive death, what would the cosmos be? A universe of hydrogen and helium almost entirely. The periodic table would be barren. No planets of rock and metal. No chemistry of carbon. No possibility for a molecule like DNA to form. The complexity we see, from a planet's geology to a cell's biology, is a gift purchased by stellar sacrifice. Paid for in entropy, delivered by the light of dying suns. Saturn's rings are a frozen moment of construction, a disk of icy fragments held in a delicate balance. They never became a moon. They stayed as a record of the process that built every planet in our solar system. This is the story of how a cloud of dust became a system of worlds. Where increasing entropy, again, is the hidden architect of order. Our solar system began as a vast, spinning disk of gas and dust around the young sun. This protoplanetary disk was a high-entropy state. Material was spread out, a chaotic mix of particles in a thin, turbulent plane. But within that chaos, an organizing principle was at work. The conservation of angular momentum. As the original cloud collapsed, its spin accelerated, flattening it into that disk. This rotation provided a scaffold, a stage for gravity to work on a smaller scale. Within the disk, microscopic dust grains began to stick together. Electrostatic forces, then simple collisions. This is accretion. It seems like building order, and it is. But each collision, each impact that welded two particles into one, was itself a messy, high-entropy event. Kinetic energy was dissipated as sound, as heat, as the fracturing of smaller pieces. The disk was a cacophony of tiny crashes, each one a minute export of disorder that allowed two bodies to become one, more ordered mass. Over millions of years, these grains became pebbles. Pebbles became boulders. Boulders became planetesimals. Bodies miles across, their gravitational pull grew stronger, sweeping up more material. The largest of these became the cores of the planets. This is where a critical boundary emerged, the frost line, a distance from the young sun where it was cold enough for water, ammonia, and methane to freeze into solid ice grains. Inside the frost line, only rock and metal could condense. This led to the small, dense terrestrial planets: Mercury, Venus, Earth, Mars. Beyond the frost line, ice was abundant. Planetesimals there could grow much larger, massive enough to capture and hold onto the vast hydrogen and helium gas from the disk. This is how the gas giants, Jupiter and Saturn, were born. They are monuments to the entropy trade. Their formation involved the catastrophic collapse of enormous gas envelopes onto solid cores, a process that released staggering amounts of gravitational energy, heating the disk and scattering material, driving entropy higher even as these ordered worlds took shape. But the young system was not serene. Evidence suggests a period called the Late Heavy Bombardment, a time, several 100 million years after the planets formed, when a gravitational reshuffling, likely caused by the migration of the giant planets, sent a storm of asteroids and comets hurtling inward. The lunar craters are its stark testimony. For Earth, this chaotic, high-entropy bombardment may have been a delivery service. It could have brought the water for our oceans and the complex organic molecules that served as precursors for life. Disorder, in a violent rain, supplied the very ingredients for a biosphere. Planetary scientist Sean Raymond often describes young planetary systems as dynamic and violent arenas. They are not static arrangements. They are systems evolving, migrating, scattering debris, in a complex gravitational dance that exports entropy through collisions and orbital changes. This leads to a quiet question about our own celestial neighborhood. The orbital stability we see today, with planets tracing predictable ellipses for billions of years, is a configuration of remarkably low entropy. It is a specific, delicate arrangement. Is this peace permanent, or is it merely a temporary calm in the solar system's long-term story? Gravitational interactions over trillion-year timescales can become unstable. Orbits can cross. Chaos can reassert itself. The ordered system of planets is a beautiful, local achievement. But like all local order, it was purchased with a currency of ancient chaos. And it may, in the distant future, repay that debt. There's this law of increasing disorder. It gave us spiral galaxies. It gave us the chemistry of life. The spark of consciousness, that's not a contradiction, it's the resolution. The second law says the total entropy of the universe always has to go up. But it doesn't say anything about local conditions. Actually, for the total to go up most efficiently, the universe often creates pockets where entropy goes down temporarily. Pockets of intense, beautiful complexity. They're not violations, they're the mechanism. The engine of global decay runs on local creation. Think of a great river. Its overall, inevitable flow is downhill. That's the increase of cosmic entropy. But within that flow, you see whirlpools, intricate, spinning eddies. They're structures of stunning local order. They form, they persist for a while, they interact, but they don't stop the river. They exist because of the river's flow. They are a way for the water to move. In that analogy, a galaxy is a whirlpool. A star is a whirlpool. A living cell is a whirlpool. Each one is a local decrease in entropy, a knot of complexity, made possible by the vast downhill rush of the universe toward disorder. For these eddies to form, you need a system kept far from calm. A river that's perfectly level and still creates nothing. The universe provides this essential tension through its expansion and cooling. The Big Bang wasn't a one-time event. It's an ongoing process. Space itself is stretching, and as it stretches, it cools. That creates a fundamental temperature difference. A gradient between the hot, dense past and the cold, dilute future. This gradient is the ultimate source of the non-equilibrium conditions that power everything. It's the reason the river is flowing downhill at all. Within this grand flow, smaller gradients arise. The difference between the hot interior of a star and the cold of space. The difference between a sunlit planet and the cosmic night. These are the specific slopes that allow for local whirlpools to spin up. They're channels for energy to flow, and for entropy to be produced in more creative ways. It's important to distinguish between mere order and true complexity. A perfect crystal of salt is highly ordered. Its atoms are in a repeating, predictable lattice. It's a state of low entropy, but it's simple, it's static. Complexity is something else. A complex system is dynamic, metastable, full of information. It has many interacting parts that produce emergent behaviors you can't predict from the parts alone. A cell isn't a crystal. A brain isn't a crystal. They're systems that maintain their structure not through rigidity, but through constant, controlled flux. They're eddies that have to keep spinning to exist. They exist on the edge, sustained by a flow. You can see this evolution in the largest structure we know, the cosmic web. In the beginning, the universe was smooth, a state of simple order. As gravity worked on the tiny ripples, it didn't create a uniform scatter of galaxies. It sculpted a vast, intricate network. Filaments of dark matter and galaxies millions of light years long. connecting at dense nodes, the great clusters, and between them immense, empty voids. This isn't random. It's a pattern of stunning complexity, a web that emerged from simple rules acting on an almost featureless beginning. It's a structure you couldn't describe with a short formula. Its algorithmic information content is enormous. Physicist Eric Chason offers a way to measure this progression. He uses a concept called energy rate density, the amount of energy flowing through a given amount of mass per second. A star has a certain energy rate density. A planet has a lower one. A living plant has a higher one than the planet. A human brain has a higher one still. It's a rough metric for complexity. It quantifies how intensively a system is processing energy to maintain its intricate, far from equilibrium state. And by this measure, the universe has been creating systems of higher and higher energy rate density over time, from galaxies to stars to planets to life. This reframes the entire cosmic story. We're not watching a slow fade to gray. We're witnessing a creative unfolding. The universe is running down, yes. But in its winding down, it's discovering breathtaking new ways to be. It's generating islands of meaning and sensation in the sea of decay. So we're left with a reflective question. One that turns the paradox inside out. As the universe exhausts its initial low-entropy fuel, as the river flows ever onward, is it not also becoming, in its most concentrated pockets, more interesting? More aware, more alive, the narrative shifts from one of inevitable decay to one of contingent, beautiful emergence. The story isn't about the heat death. It's about all the brilliant, temporary fires that light up along the way. The 19th century ran on steam, great iron engines churning and hissing. They drove everything, and that practical need how to get the most work from a given amount of heat. That was the question, an engineering question, but from the pistons and soot of that time, something else came out. One of the most profound ideas in science, the idea of entropy. It started with a French military engineer, Sadi Carnot. In 1824, he imagined an ideal heat engine. A perfect machine running in a cycle. And he saw that work could only happen when heat flowed from a hotter body to a colder one. The temperature difference was the source. His work laid the groundwork, but the universal law that was still forming. Then came Rudolf Clausius. In the 1850s, he gave it its form. He introduced the word itself, entropy, from the Greek for transformation. He stated it clearly. In any natural process, the total entropy of the universe always increases. Energy is conserved, that's the first law, but its quality degrades, that's the second. Heat dissipates, it becomes less usable. Lord Kelvin in Britain saw the same thing, the irreversible dissipation of energy. For them, the universe was a vast clockwork, winding down. And this was a staggering shift. The Newtonian cosmos had been eternal, cyclical. Now, thermodynamics showed a one-way street, leading to a final, lifeless equilibrium. A universal heat death. The cultural impact was immediate. Entropy became a symbol of cosmic pessimism, the scientific validation of decay, of an inevitable end to all activity. The historian Henry Adams, writing in the early 20th century, saw it as the perfect metaphor for his era. He saw history not as progress, but as energy dispersion. Societal decline. He wrote that the law of entropy meant the degradation of thought itself. But then came a powerful contradiction. In 1859, Charles Darwin published On the Origin of Species. Here was a theory not of decay, but of ascent. Life growing more complex, more diverse, more adapted over time. Biology told a story of progress, directly opposing the thermodynamic story of degradation. How could life build such order in a universe sliding into disorder? That conflict haunted the late 19th century. It was the great paradox. The resolution started with a shift in perspective. Led by Ludwig Boltzmann, he looked past the steam engines to the atoms themselves. In the 1870s, he developed statistical mechanics. Entropy, Boltzmann said, was not a mysterious fluid. It was a measure of probability. A state of high entropy was just the most statistically likely arrangement of atoms. A state of low entropy was a very specific, very unlikely arrangement. The second law wasn't an absolute command. It was a statement of overwhelming odds. That was a revolution. It transformed entropy from a demon of decay into a statistical tendency. It made room for fluctuations, for rare events that could give rise to local order. This statistical view led to one of the most famous thought experiments in physics. James Clerk Maxwell proposed a tiny demon, a being that could sort fast and slow molecules between two chambers. By doing that, the demon could seemingly decrease entropy without doing any work. Violating the second law. The puzzle of Maxwell's demon tormented physicists for decades. Its resolution came from linking information to physics. To decide which molecule to let through, the demon must acquire information. And storing or erasing that information, as we know from Landauer's principle, has a thermodynamic cost. It generates heat. The demon's sorting actually increases total entropy. That elegant solution showed information and thermodynamics were fundamentally linked. An insight that would blossom in the 20th century with Claude Shannon's information theory. So the understanding transformed. It moved from the practical to the profound, from a rule about steam engines to a symbol of cosmic doom, to a statistical principle of probability, and finally to a key connecting energy, information, and the emergence of complexity. The story of entropy is the story of science peeling back layers. What began as a calculation for better factory machines became the narrative thread of the cosmos. That improbable start, the wound-up spring of the cosmos. It makes you ask what wounded. That's the past hypothesis. Why did things begin with such low entropy, such order? One answer from cosmology suggests our universe might not be alone. That it could be part of a vast ensemble, a multiverse, a landscape where countless universes bubble into existence, each with random laws and random starting conditions. In an infinite sea of possibilities, a universe like ours, one that began smooth enough for galaxies and life, wasn't just possible. It was inevitable somewhere. This idea lives in eternal inflation. Imagine a primordial, unstable energy field, a false vacuum, expanding eternally, stretching at a fantastic rate. But within that expansion, tiny pockets can tunnel to a lower energy state, like bubbles in a boiling pot. Each bubble is a separate universe, pinching off from the inflating background. And the nucleation, the forming of a bubble, is random. The initial conditions inside density, geometry, entropy are set by a quantum lottery. Most bubbles might be stillborn or chaotic or barren. But with infinite tries, a small fraction will, by pure chance, start with the low entropy our universe had. We find ourselves in one of those rare bubbles not because it was designed, but because it's the only kind where beings like us could ever arise to ask. This connects to the anthropic principle. In its simplest form, it says the observed universe must be compatible with observers existing. We shouldn't be surprised to find ourselves in a universe capable of producing us. It's a selection effect. Imagine standing on an endless beach covered in stones. You look down and pick up a single, perfectly smooth, round pebble. The odds of that specific pebble being at your feet are astronomically small. But if the beach is infinite with countless stones, then somewhere a perfect pebble must exist. Your presence doesn't explain the pebble's perfection. But picking it up is only possible because you found one of the few stones smooth enough to catch your eye. Cosmologist André Linde puts it this way: in an eternally inflating multiverse, anything that can happen will happen. An infinite number of times. Our special low entropy beginning isn't a miracle. It's a statistical certainty across the whole ensemble. So does this solve the mystery? It offers a shift in perspective. The question of why our universe becomes which universe among many. The burden moves from a single special event to the properties of a larger, perhaps eternal, meta-reality. But a reflective unease often follows. Does invoking a multiverse truly answer the deep why? Or does it just relocate the mystery to an even grander, more inaccessible arena? We exchange one profound puzzle for another. That hum you hear, it's not a river, it's a data center, a warehouse of light. Billions of calculations flickering through silicon every second. This is the modern forge of information, and it's hot, blazing hot. Every search, every streamed video, every line of code processed, it's an act of creation. And all creation has to be paid for. The currency is heat. That's Landauer's principle made tangible. Physicist Rolf Landauer formulated it in the 1960s. It states a profound limit. Any logically irreversible manipulation of information, like erasing a single bit of data, must dissipate a minimum amount of heat into the environment. It's the thermodynamic cost of forgetting. When a computer resets a memory bit to 0, it has to forget whether it was a 1 or a 0 before. That act of losing information is irreversible. It increases entropy. So our digital universe, growing exponentially, isn't separate from the physical one. It's a powerful new engine for producing cosmic disorder. The more information we process, the more entropy we have to export, primarily as waste heat. This leads to the thermodynamic limits of computation. There's a fundamental energy floor. A conventional computer can't operate below it. It's set by Landauer's limit. At room temperature, that limit is extraordinarily small, about 3 zeptajoules per bit erased. For a long time, the heat from transistors switching was millions of times larger than this fundamental limit, dominated by practical inefficiencies. But as chips shrink to the atomic scale, we're approaching this boundary. The quest to overcome it led to the concept of reversible computing, pioneered by computer scientists like Charles Bennett. Reversible computing imagines a machine where no information is ever erased. Operations are designed to be logically reversible, like a perfectly elastic collision. In theory, such a computer could perform calculations with arbitrarily low energy dissipation, approaching zero heat generation if run infinitely slowly. It's a stunning idea. A computer that doesn't forget, so it doesn't have to pay the thermodynamic price. Our current technological trajectory tells a different story. Look at the evolution of the microchip. Moore's law predicted the doubling of transistors on a chip every 2 years, and it happened, delivering incredible complexity and power. But it came with a thermal crisis. More transistors packed tighter meant more heat in a smaller area. The humble microprocessor evolved, from a component cooled by air to one needing elaborate heat sinks, liquid cooling loops, immersion in specialized fluids. The growth of computational complexity has been linked to the challenge of managing its entropy export. This isn't just about keeping a laptop cool. Consider Bitcoin mining. Or training massive AI models. These are entropy export industries on a planetary scale. A single Bitcoin transaction's energy footprint can equal an average household's power consumption for weeks. That energy, drawn from the grid, ends up as heat dissipated into the atmosphere. Training a state-of-the-art, large language model requires thousands of specialized processors running for months, consuming enough electricity to power a small city. The resulting AI is a structure of immense informational complexity, but its creation required exporting a staggering amount of thermodynamic entropy into our environment. Charles Bennett offered a crucial insight. He noted it's not computation itself that requires energy dissipation. It's the act of throwing away information about the computer's past state. The heat comes from the amnesia of the machine. This reframes our digital world. Our servers and smartphones aren't just tools, they're thermodynamic systems. Engaged in the same cosmic trade as stars and cells, they take in ordered electrical energy, use it to create intricate informational structures, and export disorder as waste heat. So we arrive at a reflective question, one that ties the cosmic to the commonplace. Is the exponential growth of our information technology, the internet, big data, artificial intelligence, merely a human invention? Or is it a direct continuation of the universe's own entropy-driven complexification? Are we, through our machines, simply discovering new channels for the energy flowing through our planet to find its path toward dispersion? Creating dazzling local islands of information along the way, that hum of the server farm, it may be the sound of the cosmos thinking. The smell of rain on hot pavement, it can pull you right back to a summer afternoon years ago. You remember it, but you don't remember tomorrow. That experience isn't just a quirk. It's tied to entropy's arrow. We remember the past and not the future because of physics. Our psychological arrow of time, that feeling it flows from past to future, is tied to the thermodynamic arrow. They point the same way. In a deep sense, they're the same thing. It comes down to how correlations form. Take an egg. A whole egg in the carton is ordered low entropy. It falls and splatters on the floor, that's high entropy. The egg's contents spread out, they mix with the environment, and that spreading creates a correlation. The specific pattern of the splatter, the way the yolk sprays, the shell pieces scattered. They're all correlated with the fall. That pattern is a record. It's a memory of the event encoded in the mess. Your memory works on a similar principle. Experiences change the physical structure of your brain. They create correlations between neurons that weren't there before. Those changes are records of the past. They can only form because the universe is moving from lower to higher entropy. If entropy were decreasing, those correlations would unravel. Memories would dissolve as order spontaneously increased. A consistent record of the past would be impossible. That leads to a thought experiment, the Boltzmann brain paradox. Named for Ludwig Boltzmann, it asks a radical question. If our low-entropy universe is just a statistical fluctuation in a vast, high-entropy eternity, then what's more likely? That an entire ordered cosmos fluctuated into existence, with galaxies and planets and a long history, or that just a single, self-aware brain formed spontaneously from the chaos, complete with false memories of a past that never happened? By pure probability, a single isolated brain is a much smaller, more likely fluctuation than our entire complex universe. The paradox forces a confrontation. Are we part of a vast, coherent history? Or are we just momentary flickers of order in an endless sea of disorder, imagining a world that isn't there? Most physicists point to our universe's smooth, low-entropy beginning as evidence against the Boltzmann brain. That special initial condition. We see the thermodynamic creation of memory all around us. An archaeological dig. Layers of sediment preserve history because entropy-increasing processes, wind, water, decay, bury objects in a specific, irreversible order. The deeper layer is older because it had to be deposited before the layer above could cover it. That sequence is a direct result of time's arrow. The strata are a frozen timeline. A memory of the Earth's past written by the consistent increase of disorder. Without that one-way process, there would be no reliable archaeological record. History would be a jumble, no way to distinguish what came before what. Physicist Julian Barber has a provocative view. He's suggested that time as we feel it is an illusion. That what we perceive as the flow of time is really just a sequence of static configurations of the universe, what he calls nows. Our experience of moving through them is generated by the changing relationships between things within those configurations. In this picture, the arrow of time emerges because these nows have an intrinsic order, from low entropy to high. The feeling of moving forward is our consciousness traversing that gradient. That brings up a deeply philosophical question. If the arrow of entropy were reversed, if the universe moved from disorder to order, would our experience of time flip as well? Would we remember the future instead of the past? It's a mind-bending idea. In such a world, splattered eggs would spontaneously assemble on the floor and leap back into the carton. Memories would form of events that haven't happened yet. Your consciousness would feel like it was moving backward from our current perspective. But from within that reversed universe, it would feel perfectly normal. The inhabitants would believe they remembered the past, but that past would be our future. This isn't just sci-fi. It highlights that our entire sense of causality, of story, of a life narrative, is not a fundamental feature of reality. It's a consequence of the thermodynamic starting point. We are creatures of the gradient. Our stories are written by the universe's long, slow sigh from order into chaos. At the center of the galaxy, there's this darkness. Sagittarius, a star, a supermassive black hole. 4 million times the mass of our Sun. You don't see it. You feel its presence in the way it bends spacetime, curves it. It's not just a vacuum cleaner, it's more like a ledger, a bank for entropy. Black holes are the final state of gravitational collapse. And in that collapse, they've changed how we think about disorder. The key moment was Jacob Bekenstein, early 70s. He had a radical idea. A black hole must have entropy. And that entropy, he said, is proportional to the area of its event horizon, the point of no return. Stephen Hawking didn't like it at first, but then his own work confirmed it. Hawking found that black holes aren't completely black. Quantum effects at the horizon cause them to emit a faint radiation. Hawking radiation, which means black holes have a temperature. And if they have a temperature, they have entropy. The formula is staggeringly simple. The entropy of a black hole equals the area of its event horizon divided by a fundamental constant, times a quarter. S equals L over 4. Bekenstein-Hawking entropy. In ordinary thermodynamics, entropy is proportional to volume, more space, more ways to be disordered. But for a black hole, entropy is proportional to surface area. That's a hint about information. The holographic principle takes that hint. Physicists like Gerard T. Hooft and Leonard Susskind. It says all the information contained within a volume of space can be fully described by the physics on its boundary. The three-dimensional world we experience might be a projection from a two-dimensional surface. A black hole is the clearest example. Its entire chaotic interior, all the matter that fell in, is somehow encoded on its spherical surface. Now think about a star collapsing. A star like our Sun, over its lifetime, radiates light and produces entropy. When it dies and collapses into a white dwarf or neutron star, the entropy of that remnant is immense. But if it collapses further into a black hole, which our Sun can't do, the entropy jumps by a factor of billions upon billions. A stellar mass black hole contains more entropy than every star, planet, and particle in our entire galaxy combined. It's the most efficient entropy storage device physics allows. That leads to the strange fate of black holes themselves. Evaporation through Hawking radiation. Empty space isn't empty. It seethes with quantum fluctuations, virtual particle pairs popping in and out of existence. At the edge of an event horizon, one particle can fall in while its partner escapes. To an outside observer, the black hole just emitted a particle. This process slowly saps the black hole's mass. Over timescales far longer than the current age of the universe, the black hole shrinks. Eventually vanishes in a final burst. And this evaporation increases the total entropy of the universe. The highly ordered, low-entropy state of a massive black hole becomes a diffuse cloud of Hawking radiation. A state of much higher entropy. Even in its death, a black hole serves the second law. Then there's the question of information. Imagine throwing a book into a black hole. The book is incinerated, torn apart, atoms crushed. Hawking's early calculations said the radiation emitted is purely thermal. It carries no information about what fell in. The information in the book would be lost forever. That violates quantum mechanics. The black hole information paradox. Leonard Susskind and others have a resolution. The information isn't lost. It's scrambled, encoded onto the event horizon in unimaginably complex ways, then slowly released in the Hawking radiation. The process is chaotic, irreversible, like burning a book to ash and smoke. You couldn't reconstruct the book from the smoke, but in principle, all the information is still there. In the correlations between the emitted particles, the black hole is the ultimate scrambler of information, maximizing entropy before that information is reluctantly returned. So look to the far future. trillions upon trillions of years from now, all stars burned out, galaxies evaporated. The universe becomes a dark, dilute sea of particles and photons, creeping toward absolute zero. In that era, the only significant structures left will be black holes, and for an epoch longer than we can comprehend, they'll be the dominant repositories of cosmic entropy, slowly leaking their stored disorder back into the void through Hawking radiation. They are the endgame of gravitational structure, the final monuments to the universe's capacity for creating order, now serving as its ultimate sinks for decay. That vision forces a question about our own moment. Are we living in a brief, bright flowering of complexity, nestled between a smooth beginning and a dark, simple end? Or is this story of creation from decay an eternal cycle, playing out in ways we haven't yet imagined? That final burst from the last black hole fades out, and then it's just dark. The universe enters its final era, this profound quiet, the heat death, the big freeze. It's not an explosion, it's not a collapse. It's this slow, irreversible sigh into equilibrium, the ultimate high-entropy state, where no meaningful temperature differences exist. No hills left for energy to roll down, no gradients to drive a whirlpool or a star or a thought. It's the logical endpoint of the second law, in a cosmos forever expanding under dark energy. The timeline to get there is almost beyond comprehension. We're not talking billions of years, we're talking trillions, then quadrillions, then googolls of years. The first major phase is the end of starlight. In about 100 trillion years, the last stars, the red dwarfs, the frugal burners, they finally exhaust their fuel. Nuclear fusion ceases in the cosmos. What's left are galaxies of stellar remnants, white dwarfs, neutron stars, cold planets, and then, over even longer times, gravitational encounters fling these objects out into the void. The galaxies slowly evaporate. The universe becomes a scattered graveyard of dark, dense objects, drifting apart in an ever-accelerating expansion. Then comes the decay of matter itself. Current physics suggests protons might not be perfectly stable. Over timescales around 10 to the 34th years, protons could spontaneously decay into lighter particles. If that happens, every white dwarf, every neutron star, every frozen planet dissolves into a diffuse sea of electrons, positrons, photons, neutrinos. All complex structure built from atoms vanishes. The final act belongs to black holes. They're the last islands of low entropy, and they succumb too. Through Hawking radiation, that slow leak, a stellar mass black hole might evaporate in 10 to the 67th years. The supermassive ones at galactic centers could take 10 to the 100th years. Or longer. Their evaporation is the universe's last significant event. That produces entropy. When the last black hole winks out, the cosmos contains only this thin, cold soup of fundamental particles and radiation, stretched across an infinite, ever-cooling volume. This is the equilibrium. Picture a cup of hot coffee, left in the center of a vast, perfectly insulated room. At first, the heat flows from the cup into the cooler air. It creates currents, eddies, complexity, but given enough time, the heat spreads uniformly. The coffee reaches room temperature. The air is still. No further movement is possible. The entire system is at maximum entropy. The universe, in its heat death, is that room. And every galaxy, every star, every living thing was a temporary eddy. In that long, final cooling, there are alternative futures, speculative ones, the Big Rip scenario. If dark energy's repulsive force grows stronger, it could eventually tear apart galaxies, stars, planets, even atoms, in a final, catastrophic dissolution. Vacuum decay posits our universe might exist in a metastable state. A false vacuum. A quantum event could trigger a bubble of a more stable vacuum to form and expand at light speed, rewriting the fundamental laws of physics in its wake, erasing all structure. But even these dramatic ends lead to a form of featureless equilibrium. Faced with this, physicist Freeman Dyson once asked a question: Could a form of eternal consciousness survive? A society of vastly advanced beings or uploaded minds? His theoretical work suggested that by operating in slower and slower cycles, using less and less energy, information processing could continue forever. Even as the temperature approaches absolute zero, it's a staggering thought that sentience might persist as the last flicker of structure, adapting to the spreading dark. Finding meaning in thoughts stretched across eons, this projection forces a confrontation with our paradox. If the cosmos is destined for this silent equilibrium, does that make the transient complexity we see more or less meaningful? The galaxies, the planets, the life, the love, the art. One perspective sees a tragic futility. All this grandeur, all this struggle, just a fleeting spark in an endless night. Destined to be forgotten. But the other perspective, forged through understanding entropy's creative role, offers a different answer. The heat death is not the point. The meaning is not in the final, silent state. It's in the magnificent, improbable journey, from that smooth beginning to that flat end. The universe's story is the story of the eddies. The whirlpools of order that form, spin, interact, and glow with sensation for a time, precisely because the river is flowing downhill. Our existence, our consciousness, is the universe experiencing its own winding down. In the most intimate way possible, we are not just passengers on this journey, we are the journey becoming aware of itself. The heat death is the destination. But the meaning is written in every star that ever burned, every cell that ever divided, and every mind that ever wondered why. Jackson Pollock's paint drips and splatters. It looks like chaos frozen, but from that chaos comes a kind of order, a beauty that feels random and intentional at the same time, and that's an echo of the cosmic process. Long before physics named it, artists were already dealing with entropy, not as a formula, as a metaphor. They felt it in crumbling ruins, in fading frescoes. In the slow change of all things, they sensed creation and decay were linked. That beauty lives in impermanence. Think of ancient ruins, we don't see them as failures. We see a beauty in their return to the earth. Vines on stone, weather-smoothing edges. That decay is a narrative. It tells the story of time, of one order surrendering to another. In Japanese culture, this is wabi-sabi. Beauty in the impermanent, the imperfect. A cracked bowl repaired with gold. Moss on a garden stone. The patina on a bronze statue. That green-blue surface isn't a flaw. It's a record. A chemical conversation between metal and air and time. A slow, entropic transformation. The statue becomes more itself through decay. Some artists invite entropy in. The composer John Cage used chance operations. He consulted the I Ching to determine notes. He used randomness as a creative partner to find new forms of order that intention alone couldn't reach. His silent piece, 4 minutes 33 seconds, frames the ambient sounds of a concert hall. It turns the entropy of the environment into the music. In literature, Thomas Pynchon wove entropy into his novels. His early story, Entropy, uses it as a metaphor for the decay of communication, the breakdown of relationships, the slow heat death of social systems. His characters struggle against a world sliding into disorder. Yet they find moments of meaning within that slide. Pynchon saw entropy as the human condition, a background hum of loss. The land artist Robert Smithson took this to the landscape. He built the spiral jetty in Utah's Great Salt Lake, a massive coil of rock and earth. He didn't see it as permanent, he welcomed the elements. The salt water would encrust it, change its color, transform it. He wrote that entropy was a condition art could mirror, that it moves toward a gradual equilibrium. His art was a collaboration with that process. So there's a question here. Does human creativity mimic the universe's own method? We don't create from nothing. We take the chaos of experience, the random stimuli of the world. We channel that flow, we organize it, we make a local pocket of meaning, a poem, a symphony, a theory, a temporary eddy of complexity, and in doing that, we export our own disorder. The discarded drafts, the failed experiments. Our art is a dissipative structure, sustained by the flow of life through us. The human impulse to make meaning isn't separate from the cosmic drive toward dispersion. It might be its most poignant expression, a way for the universe to not just wind down but to feel its own winding down, through us, a city in the morning, breathing out that warm cloud. The power plants running, the traffic starting up. That's us, exporting entropy. On this planet, we're the ones creating local order. And that act of creation, it has an ethical side to it because of the second law. We're responsible for the disorder we make. It's a thermodynamic responsibility. And this isn't just a metaphor for our civilization. It's a practical way to see sustainability. To understand how we use resources, how we care for the environment, you can look at any industrial process, any economic deal, through this lens of entropy production. The heat from a server farm, the pollution in a river, the plastic gathering in the ocean, these aren't just byproducts, they're the exported entropy of our complex society. The bill coming due for the local order we've built. To see it, you can look at two kinds of economy. The first is the linear economy. You take resources from the earth, you make products, you throw them away as waste. It's a high-entropy system. It treats the planet like an infinite source of low-entropy materials and an infinite dump for high-entropy waste. But the earth isn't either of those things. It's a closed system for matter. So the linear model, it maximizes short-term local order, our cities, our stuff, but it violently speeds up global disorder. Pollution, habitat loss, resources running out. The second model is the circular economy. Designed to cut waste, to keep materials in use, it mimics natural cycles. Here, waste from one process becomes the input for another. It aims for a lower entropy flow. It accepts that every act of creation has to account for its own decay. And the big challenge of climate change at its heart is a thermodynamic and ethical problem of entropy management. We burn fossil fuels, which are these highly ordered stores of ancient sunlight. We turn them into useful work, into complex structures, but the export is carbon dioxide and waste heat. That carbon dioxide acts like a blanket, trapping more of the sun's energy inside our planetary system. It messes with the delicate gradient that keeps our climate far from equilibrium. We're clogging our planet's main channel for exporting entropy back out into space. So the ethical question becomes, how do we keep building human flourishing without degrading the very gradients that make life possible? This perspective was laid out by the economist Nicholas Georgescu-Roegen. Back in the 1970s, he argued that economic processes are fundamentally entropic. The economy, he said, feeds on low-entropy matter and energy from the environment, and it spews out high-entropy waste. He thought mainstream economics was flawed for ignoring this physical bedrock. Growth couldn't be infinite on a finite planet, because we'd exhaust the low-entropy resources and overwhelm the sinks. His work, it's debated, but it forces a reframing. Wealth isn't just money. It's the accumulated stock of low-entropy, useful order we have available. And we're spending that inherited cosmic capital at a staggering rate, which leads to a practical question for our time. Is a sustainable civilization one that learns to optimize its local complexity, its art, its science, its community, while meticulously minimizing and managing its negative entropy export on a planetary scale? Can we design our cities, our industries, our lives to be beautiful, efficient eddies in the energy flow, without churning the river into a destructive flood? The answer won't be in a single law of physics. It'll be in the choices we make. Recognizing we're not outside the thermodynamic story, we're its most conscious chapters so far. You see a flock of starlings moving together. It's like one thing swirling in the sky. There's no leader, there's no plan, but each bird is just doing a few simple things. Follow the neighbor, don't crash, stay close, and from that, this complex flowing pattern appears. That's not magic, it's something the universe does. It happens at every scale. It's called self-organization, and what comes out of it is emergence. Systems full of energy flow, driven by entropy, they can make these pockets of order. On their own, so, self-organization, that's when a system with lots of parts interacting gets pushed away from equilibrium, and it arranges itself into a pattern. No outside hand, and emergence is what you get. It's the properties, the behaviors that show up at the group level. You couldn't predict them by looking at one part alone. The flock's intelligence isn't in any one bird. It comes from how they all interact. This is physics and statistics, in a world that's not calm. It needs a constant flow of energy to keep going. And it runs on a few principles. Feedback loops are central. Positive feedback amplifies a change. Negative feedback dampens it, like in a pan of oil on the stove. A little unevenness gets amplified. Hot fluid rises, cold sinks, that creates a roll, and that roll reinforces itself. You end up with these hexagonal patterns. Baynard cells. A simple temperature gradient makes geometric order. Another principle is criticality. The system gets poised at a threshold, where a small change can trigger a big reorganization. Think of a sandpile. You add grains, it builds up. Then one more grain causes an avalanche. The pile organizes itself to that critical state, where avalanches of any size can happen. That scale invariant behavior shows up in earthquake faults, in forest fires, in the firing patterns of neurons in your brain. The system tunes itself to the edge of chaos. That's where complexity lives. Then there are phase transitions, the dramatic shift between states. Water to ice is one, but in complex systems you see it in social behavior. In traffic flow, in ecological populations, these shifts often mean a new, coherent structure is emerging from disorder. You see this everywhere, the spiral arms of a galaxy. That's an emergent structure. It comes from the gravitational interactions of billions of stars and gas clouds, just following the law of gravity in a rotating disk. No architect, it's self-organized, the origin of life, that might be the ultimate emergence. In the primordial soup, simple molecules interacted. They catalyzed reactions. Formed cycles. Some sets of molecules were better at capturing energy and replicating. Through feedback and selection, they got more complex. Eventually, they crossed a fuzzy line into what we'd call living. They were dissipative structures, organized not in spite of the second law, but because they were good at exporting entropy. Or a single snowflake. It starts as a speck of dust. Water vapor freezes onto it, but its path through the atmosphere, through different temperatures and humidity, that governs how the arms branch. The six-fold symmetry is from the crystal structure of ice, but the intricate, lace-like detail of each unique flake, that's an emergent record, a physical memory of its journey. Written in ice, its order born from a flow of energy and matter under specific, changing conditions. Stuart Kauffman called this order for free. He said in complex networks of chemical reactions, self-sustaining cycles will inevitably arise. So order isn't a miraculous accident in a universe of decay. It's a natural product of the universe's own dynamics. We are at home in the universe, he said. Its laws spontaneously generate the complexity that leads to beings like us. That perspective raises a question. Is the whole cosmos, from quantum foam to the cosmic web, engaged in one grand process of self-organization? Are the swirling galaxy, the circulating atmosphere, the flock of birds, and the firing network of a human brain, are they all different versions of the same principle? Where energy flow, guided by simple rules and feedback, gives rise to endless forms of emergent order. If that's true, then understanding the universe isn't just about taking it apart. It's about learning to see the patterns it is constantly weaving into being. That image, the pale blue dot, it's a world hanging in a sunbeam, and it makes you ask, are we alone, or are there other islands like it out there? Now the search for an answer, it's guided by something unexpected. The laws of thermodynamics. We're not just looking for life. We're looking for signs of entropy reduction, sustained. Like a persistent whirlpool in the cosmic flow. Biosignatures, those chemical hints, they're really thermodynamic signatures. A planet in pure chemical equilibrium, all its gases mixed and reacted. That's a high-entropy world. A dead world. Life is a disequilibrium engine. It pushes a system away from that uniformity. Take the oxygen in Earth's air. Oxygen is reactive. Left alone, it would bind with rocks and vanish. Its persistent presence here is an anomaly, a state of low entropy maintained by photosynthesis, which uses solar energy to split water and pump oxygen into the air. Astrobiologists like Sarah Seeger, they focus on these atmospheric imbalances, unexpected gas combinations that should react but don't. That's a promising sign of life. This thinking reshapes the Drake equation, which estimates civilizations. Several of its terms are thermodynamic, the fraction of planets with right conditions. It's not just about distance from a star. It's about whether a planet can maintain a persistent energy gradient, a temperature difference, a chemical disequilibrium, stable enough, long enough for complexity to emerge. And the lifetime of a civilization may hinge on managing the entropy it produces, avoiding poisoning its own gradients. The search goes beyond biology to intelligence. Technosignatures are the entropy footprints of a building civilization. We might detect artificial lights on the night side of an exoplanet, an export of organized energy into darkness, or industrial pollutants in an alien atmosphere. Certain synthetic chemicals like chlorofluorocarbons, they have no natural source. Their presence would be a low-entropy fingerprint, a sign that something is imposing a specific, unlikely order on matter, at a massive entropic cost. Even the structure of energy use could betray a presence. A natural planet radiates heat in a smooth, predictable profile. A technological world with cities and computation would have a more complex infrared signature. Patches of unusual warmth, emission patterns that don't match any natural process. From a distance, it would look like a fever of creativity on the surface. So we scan spectra of distant atmospheres. We listen for structured radio signals, all seeking the same underlying pattern, evidence of a system fighting equilibrium. This frames the ultimate question in terms of universal physics, not just biology. If we one day confirm another pale blue dot, will its story be the same? Will its life, its intelligence, also be a rebellion against dispersion? A way for that corner of the universe to experience its own winding down with sensation and story. Finding company would mean the paradox isn't ours alone. It's woven into reality wherever complexity dares to arise. The double-slit experiment. You fire a single particle at a barrier with two slits. And it doesn't go through one slit or the other. It goes through both. It exists as a wave of probability, a superposition of all possible paths. It only becomes a single definite particle when we measure it. When we look, that's the bedrock, and it makes you ask what order even means in a world built on probability. At that scale, a definite state dissolves. It's just a haze of possibilities, and that's where entropy begins, not with heat but with information. The classical world, with its definite temperatures and pressures, emerges from this quantum fog. Through a process called decoherence, a quantum system, if it's perfectly isolated, can stay in superposition. But nothing is perfectly isolated. The tiniest interaction with the environment acts like a measurement. It forces the system to choose, to collapse from many possibilities into one actuality. That irreversible loss of quantum coherence is an increase in entropy. It's the moment probability crystallizes into fact, and it exports information into the environment, spreading disorder. Decoherence is why we see a definite world. It's the quantum reason times arrow exists. To quantify this, we use von Neumann entropy, the quantum version of thermodynamic entropy. Instead of counting particle arrangements, it measures the mixedness of a quantum state. A pure state, a perfect superposition, has zero von Neumann entropy. A fully mixed state where all quantum information is lost has maximum entropy. The journey from pure to mixed, driven by decoherence, is the microscopic story of the second law. This leads to quantum entanglement. When two particles become entangled, their properties are linked. Measuring one instantly determines the state of the other. That connection stores information in a non-local way. But when an entangled system interacts with the environment, that web of correlations gets shredded. The information leaks out, becoming noise. The entanglement entropy increases. Some physicists suggest this dispersal of quantum information is the most fundamental form of entropy increase. The thermodynamic entropy we see might just be the large-scale echo of quantum correlations dissolving. You can see this in a modern double-slit experiment. If you don't record which slit the particle goes through, you get an interference pattern. That's the wave-like behavior. But if you place a detector to gain that information, to know the path, the interference pattern vanishes. You get two clumps. Particle-like behavior. The act of gaining information destroyed the quantum coherence. It increased the entropy. The knowledge came at the cost of possibility. This idea inspired John Wheeler's phrase, "it from bit." He proposed that everything in the universe derives from binary yes or no answers, from bits of information. Physics becomes information theory. The universe is a vast network of information exchange, and entropy is the measure of information that's become lost or scrambled. The implications reach into the cosmos. Those tiny ripples in the early universe, the seeds for galaxies, were likely born as quantum fluctuations, microscopic uncertainties stretched to cosmic size by inflation. The entire large-scale structure of the universe is quantum probability writ large across the sky. The initial low entropy of the smooth plasma was a specific, unlikely outcome of a quantum lottery. In black hole physics, von Neumann entropy becomes central. The Bekenstein-Hawking entropy, proportional to the event horizon's area, is understood as a measure of the quantum information hidden by the horizon. The black hole information paradox is a crisis about whether this quantum information is truly lost. And in quantum computing, entropy is the enemy. A quantum computer relies on maintaining delicate superpositions. Qubits in a state of pure, low von Neumann entropy. Decoherence is the constant threat. The heat and noise of the environment constantly try to measure the qubits, collapsing them, increasing their entropy, and ruining the calculation. Building a quantum computer is a fight against the thermodynamic arrow, a battle to preserve quantum order. So we're left with a question. If our classical world of cause and effect emerges from a quantum foundation of sheer probability, does that mean entropy itself is not fundamental? Is the relentless increase of disorder we experience just the statistical tendency of quantum information to leak and scatter, to become forgotten? Does the quantum realm hold the key, showing us that order precipitates from a sea of probability, only to be dissolved back into it, in an endless cycle? From that quantum haze, our own world came together, became this breathing hole, and from space, Earth isn't just a planet, it's an engine, a single system built to process sunlight. This blue marble, full of life, is our closest look at planetary entropy. Every forest, every ocean current, every wind is part of a machine. It captures low-entropy solar energy and sends high-entropy infrared heat back out. The whole biosphere is a dissipative structure, planetary in scale, and at the center is photosynthesis. That's the primary pump. Leaves are like tiny green portals. They catch the high-energy photons from the sun. They use that ordered energy for a kind of alchemy, taking carbon dioxide and water, simple disordered molecules, and weaving them into complex sugars. That's a local decrease in entropy, but the process pays a debt. It releases oxygen and waste heat. The plant grows. It becomes structure and fuel for the entire food web. From insects to elephants, every consumer is part of this. They convert that captured order into motion, into warmth, and finally into infrared radiation that escapes to space. The biosphere is spectacularly good at this export. This gives a thermodynamic lens to the Gaia hypothesis, from chemist James Lovelock. He saw Earth not as a rock with life on it, but as a single, self-regulating system. In entropy terms, life isn't a passenger. It actively shapes the environment, the air, the ocean's salinity, the global temperature. It maintains the conditions that sustain this massive energy flow. It optimizes the planet for entropy production. Take the carbon cycle. That's a planetary entropy transfer mechanism. Carbon moves from the air into plants, into animals, into soil, into oceans, and back. Each transfer involves energy conversions. Each step dissipates some heat. Then there are ocean currents and atmospheric circulation. They're like the planet's circulatory system. They move heat from the warm equator to the cold poles. These great conveyor belts are driven by temperature and salinity differences. They are machines for smoothing out gradients. For exporting entropy, you can see this engine pulse with the seasons. Watch a satellite time-lapse over a year. The great green wave of spring and summer across the continents. That's a visible explosion of biological order. A massive act of entropy reduction as sunlight is captured and stored. Then comes autumn and winter. The decay. Leaves fall and decompose. The stored energy is released by microbes and fungi, slowly radiating away as heat. This annual rhythm is the planetary breath. An inhale of order, an exhale of disorder. Driven by the tilt of the Earth and the relentless gradient of the Sun. Now human activity enters this system. We're altering these global entropy flows. Land use change, clearing forests for farms or cities, replaces a complex, high biomass system with a simpler one. It changes how that patch of Earth absorbs light and radiates heat. More profoundly, burning fossil fuels is like opening a geologic vent. We're tapping into an ancient store of low-entropy sunlight. Captured by plants millions of years ago and compressed into coal and oil. We burn it in an instant. We use it to build our world, but we export the entropy not just as heat. As a sudden, massive pulse of carbon dioxide into the air. This alters the planet's radiative balance. It thickens the blanket, impeding Earth's ability to export entropy smoothly back to space. We are, in thermodynamic terms, clogging the engine. Lovelock described Earth as a living system that maintains conditions for life. From our perspective, we might ask a different question. Is a living planet inherently more efficient at dissipating solar entropy than a dead, rocky one? A barren world like Mars just reflects some sunlight and radiates heat based on its temperature. But Earth, with its swirling clouds, its deep green forests, its churning oceans full of life, processes that incoming energy through countless layers of transformation. It creates temporary, magnificent structures, a coral reef, a rainforest. They are intermediate steps in that grand dissipation. The living planet seems to find more creative pathways for the sunlight to degrade. It turns a simple flow into a symphony of decay. So when we look at that pale blue dot, we're not just looking at our home, we're looking at a cosmic example of how matter and energy, given the right conditions, can organize into a self-sustaining whirlpool of complexity, all while serving the universe's most fundamental directive. A civilization could build a sphere around its star, a Dyson sphere, but it wouldn't be a solid shell, it would be a swarm, a vast swarm of orbiting collectors capturing sunlight. Every photon, it sounds like science fiction, but it's a kind of thermodynamic necessity for any intelligence that keeps growing, a Kardashev Type 2 civilization. One that harnesses the entire energy of its star. They wouldn't do this just for power. They'd do it to fuel the next leap, a leap in complexity, to create a computational substrate. On an unimaginable scale, this is post-biological evolution. The drive for complexification, once carried in DNA, passes to synthetic minds, to self-replicating machines. Unconstrained by biology, these agents could think on timescales of millennia. They could manipulate matter on the scale of solar systems. Their projects would be the ultimate expression. Entropy-driven creation, turning stellar fury into structured thought. The most profound concept here is the Matryoshka brain, those Dyson swarm collectors. They don't just make electricity. They power a nested series of computational layers. The outermost layer runs cool. It uses waste heat from the inner layers. Each layer processes information. Its waste heat fuels the next. It's a computational onion built around a star, a single planet-sized mind, or a vast civilization of uploaded consciousnesses. Its purpose is to think thoughts too vast for any organic brain, to simulate realities, to solve cosmic mysteries. It exists for one reason: to process information at a stellar scale. And in doing that, it would radiate a distinctive signature, an infrared signature into space, a star-dim invisible light but glowing with waste heat. The waste heat of colossal computation, that could be a detectable technosignature, a beacon not of communication but of pure activity, entropic activity. This thinking scales up further. A Kardashev Type 3 civilization harnesses the energy of a galaxy. Its projects become galactic engineering. One speculative idea is star lifting. A society that advanced might not just collect a star's light. They might actively mine it, using magnetic fields to siphon off plasma, to extend the star's lifespan by reducing its mass, or to gather raw materials for building more computational infrastructure. They would be stellar gardeners, pruning and tending suns, to maximize the long-term energy flow. The ultimate energy source and the ultimate waste dump might be a black hole, a rotating black hole, a Kerr black hole. It stores an enormous amount of rotational energy outside its event horizon. That energy could be extracted through the Penrose process or by harvesting radiation from an accretion disk, and a black hole is a perfect entropy sink. A civilization could feed it waste matter, the ultimate recycling center, where disorder is swallowed by an object whose entropy is defined by its surface area. A black hole civilization, as envisioned by someone like Ray Kurzweil, might use this not just for power, but for computation. Kurzweil has speculated that intelligence will eventually saturate the universe, turning matter into optimized substrates for experience, for understanding. This isn't about conquest. It's about the universe waking up, becoming self-aware. Self-engineering. The thermodynamic requirements for this are astronomical. They presume a mastery of matter that seems magical, but they follow a logical progression. From the principles we know, life lowered entropy locally to build complex structures. Intelligence found ways to lower it further, to build cities and computers. A post-biological intelligence with millennia to plan would seek to optimize this process on a stellar scale, to create the most complex structures physically possible, all while managing the colossal entropy export that requires. Their megastructures would be dissipative structures of the highest order, whirlpools in the galactic energy flow. So we're left with a question, a speculative one. As we look at stellar nurseries and ancient galaxies, could the universe's final structures be intentional? Not just the blind work of gravity and chemistry, but the deliberate creations of an intelligence that emerged from that blind work. Could the long-term story be one where the universe, through life and then mind, gradually learns to shape itself, to turn its own winding down into an art form? If so, then the paradox finds its resolution. Entropy's increase isn't the end of meaning, it's the canvas. The canvas upon which meaning, grown conscious, might paint its final works. The laws of physics tell one story. It's a unified story, far simpler than it seems. Thermodynamics, gravity, quantum mechanics, information theory, they are not separate. They are threads in a single narrative. The universe moves from simplicity to complexity. And it's driven by one thing, the increase of entropy. That's the hidden structure of everything. The expansion of space creates the ultimate temperature gradient. It's a grand non-equilibrium, and gravity uses that gradient. It sculpts smooth potential into structured mass. It pays for that local order by sending a massive amount of radiant disorder out into the void. Quantum mechanics gives us the probabilistic foundation. Decoherence happens the loss of quantum information, and that becomes the microscopic engine for the thermodynamic arrow. Information theory gives us the language. It shows that every complex structure is a packet of information. A DNA molecule, a galactic filament. They are specific configurations carved from randomness. Take a star. Its life cycle begins with quantum fluctuations stretched to a cosmic scale. They seed a slight unevenness in a gas cloud. Gravity takes over. It converts gravitational potential into the chaotic heat of collapse. Nuclear fusion ignites. That process is governed by quantum tunneling. It transforms simple hydrogen into heavier elements. The star shines. It's a dissipative structure, radiating entropy into the void for billions of years. Then it dies in a supernova. That's a catastrophic entropy event. It forges the complex atoms of chemistry and scatters them into space. Later, those atoms form planets. On at least one planet, they become the substrate for self-replicating molecules. For life is another exquisite form of entropy export. It's one coherent arc, from quantum probability to biological complexity, linked by the flow of energy toward dispersion. Black holes aren't exceptions to this unity. They're its ultimate expression. Their immense entropy is proportional to their surface area. That ties gravity to thermodynamics and information in the most profound way. Their eventual evaporation through Hawking radiation is the final act. Quantum information returns to the universe. It completes the cycle. Even our own consciousness fits this framework. It's a whirlpool of electrochemical processing, a metastable pattern sustained by a constant flow of energy. It creates a rich inner world of experience while exporting metabolic heat. The universe, through us, becomes aware of its own story. Albert Einstein once marveled at this. He said the most incomprehensible thing about the universe is that it is comprehensible. We can trace the logic from the first microsecond to the firing of a neuron because the same sparse set of rules applies everywhere. The universe isn't a collection of unrelated phenomena. It's a single, evolving equation. So we're left with a synthesizing question. Does the relentless increase of entropy explain why our universe is so richly complex? It's not in spite of the drift toward disorder. It's precisely because of it. Stars ignite because of it. Planets form, life adapts, minds wonder. The drive toward maximum entropy creates the gradients. It creates the flows, and it creates the temporary islands of order where complexity can flourish. In this light, the entire cosmic epic might be seen as entropy's method. From the first hydrogen atom to the last thought in a distant civilization, it's entropy finding the most creative paths to its own increase. You're a temporary arrangement of atoms, a configuration the universe has gathered for a while. You're a pocket of order, a local defiance against the spreading tide of disorder. You exist because you consume free energy, sunlight stored in food, and you export warmth molecules back into the world. That thermodynamic fact carries weight. It means your consciousness, your creativity, your sense of self, it's a transient eddy in the universal flow toward equilibrium. That perspective can feel overwhelming, but it also offers a clarity about what it means to be here. Think about impermanence. Everything you are is borrowed. The atoms in your hand were forged in a star that died before our sun was born. They scattered, gathered by gravity, woven into the chemistry of our planet. Then, through life's machinery, assembled into you. They are on loan. One day, that specific configuration will dissolve. The energy flow that sustains you will stop. The eddy smooths out. That's not morbid, it's physical. It frames your existence not as a permanent fixture, but as an event. A brilliant, temporary event. Like a campfire in the vast night. The fire is a structure of fierce order. It transforms wood into light and heat. It crackles with complexity, but it burns its fuel. It produces ash, warm air that rises and disperses. It's destined to go out. Yet, while it burns, it provides light. Warmth to gather around, a focal point for stories, for connection. Its value isn't diminished by its end. Its transience is the source of its beauty, its purpose. This connects to legacy. If we're temporary whirlpools in the cosmic river, what matters is the shape of our whirlpool. The effect it has on the flow around it. The order we create, a kind word, a solved problem, a piece of art, a nurtured relationship. These are local decreases in entropy. They are improbable, meaningful structures we introduce into the world. They ripple outward. Long after our personal configuration dissolves, the patterns we created can persist. In memories, in knowledge shared, in the love we put into the world, we can't fight the universe's final equilibrium, but we can shape the journey toward it. We can make the gradient of our lives yield not just waste heat, but light. Astronomer Carl Sagan reflected on the pale blue dot image of Earth. He said our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there's no hint that help will come from elsewhere to save us from ourselves. It is up to us. He added, to him, it underscores our responsibility to deal more kindly with one another. To preserve and cherish the pale blue dot, the only home we've ever known. That kindness, that cherishing, is the ethical response to understanding our thermodynamic fragility. We are all the same rare type of temporary order, sustained by the same thin flow of energy on the same vulnerable world. So this brings the cosmic paradox down to the personal. To the quiet moments of your life. Knowing you're a product of this universe's magnificent, entropy-driven creativity, how does it change the way you value your time? Your attention, your actions, you're not a bystander to the cosmic story. You are its current, conscious expression. The universe is winding down, yes. But in you and through you it is also winding up. Into sensation, into story, into meaning. That's the trade. The profound and precious trade at the heart of existence. Maxwell had this thought experiment. A tiny demon at a door between two gas chambers. It watches molecules. If a fast, hot one comes from the left, it opens the door, lets it go to the right. If a slow, cold one comes from the right, it lets it pass to the left. The demon isn't doing work, it's just sorting. Over time, the left side gets colder. The right side gets hotter. A temperature difference appears from nothing. That seems to decrease entropy. It seems to violate the second law. The resolution came from information. To sort the molecules, the demon has to observe them. It has to acquire information about their speed and position. That information isn't free. To make a decision, the demon has to erase its old memory of the previous molecule. To make room for the new data. And erasing information, as Landauer showed, has a cost. A thermodynamic cost. It generates heat. That heat increases the entropy of the demon's environment. By more than the sorting decreases the entropy of the gas. Total entropy still goes up. The demon isn't cheating, it's part of the system and it pays the bill. Information is physical. Then there's a stranger thought. In a vast, eternal, high-entropy universe, statistical fluctuations have to happen. Given enough time, anything with a non-zero probability will occur. So what's more likely? That an entire ordered universe like ours fluctuated into existence from chaos? Or that just a single, self-aware brain, with all its memories and senses, just formed spontaneously from random particles? That's the Boltzmann brain paradox. It suggests disembodied brains should vastly outnumber beings like us. Beings part of a long, coherent history. Our experience of a consistent past could be an illusion. A false memory from a random fluctuation. This paradox isn't taken as reality. It's a check on our theories. It tells us our universe's smooth, low-entropy beginning isn't just a lucky break. It's a necessary starting condition. It steers cosmic history away from those statistical ghosts. Our reality isn't a fleeting hallucination in an eternal sea of disorder. You can see entropy's arrow at home. Take two clear cups. Fill one with very hot water, the other with very cold water. Add a drop of food coloring to each. Watch. In the hot cup, the dye swirls and spreads fast. A turbulent dance. In the cold cup, it drifts slowly. Now pour the hot water into the cold water. For a moment you see streaks, distinct regions of different temperatures, but watch, the streaks blur, the colors mix, the water reaches a single, uniform lukewarm temperature. Now try to unmix them. Try to get the hot molecules back into one cup and the cold into the other. You can't. The process is irreversible. You've created entropy. The system moved from order, two separate temperatures, to disorder, a single temperature. The energy has spread out. There's no spontaneous way to concentrate it again without doing more work. Like using a refrigerator, which would export even more entropy elsewhere. This irreversible mixing points to a deeper puzzle, Loschmidt's paradox. The fundamental laws of physics are time-symmetric. Newton's mechanics, quantum electrodynamics. If you filmed two billiard balls colliding and rolling apart, and played the film backwards, the reversed motion would also obey the laws. The equations work just as well forwards and backwards in time. So why don't we see a broken egg reassemble? Why does time have a definite arrow? The resolution is in the initial conditions. The universe started in a state of fantastically low entropy. The laws are reversible, but the starting point was not. Given that special beginning, the most probable path forward is toward higher entropy. Playing the film of cosmic history, backwards would show a progression from high entropy to low entropy, which would be astronomically improbable given any random starting point. The arrow of time is baked into the initial state of everything. Other examples are everywhere. Watch cream diffuse in coffee. The swirling white clouds slowly fade into a uniform tan. That's entropy increasing. The cream molecules, initially concentrated, explore every possible position, moving toward the most probable mixed state. Or with a physics simulation, you can model gravitational collapse. Start with a cloud of dots, particles distributed almost uniformly, set gravity to act between them. Run the simulation, you'll see tiny initial ripples amplify. The cloud will clump, forming structures, while sending some particles flying away at high speed. The system creates local order, the clumps. But the total entropy, when you account for the energy of those fast-moving ejected particles, has increased dramatically. The classic analogy is a shuffled deck of cards. A new deck in perfect order is a low-entropy state. There's only one way for it to be in that exact sequence. Shuffle it once. The cards are now in a random sequence, one of an unimaginably vast number of possible arrangements. That's high entropy. The deck will almost never shuffle itself back into perfect order by chance. The move from order to disorder is a one-way street driven by probability. Richard Feynman had a beautiful approach to learning this. He said you don't truly understand something unless you can explain it to a freshman. Or build a model of it, or see it in the world around you. It's about curiosity, asking simple questions and following them to profound answers. Why is the sky blue? Why does a mirror reverse left and right but not up and down? These questions lead you into the heart of physics. So here's a question, a chance to apply this curiosity. Look at your own day. Can you think of an example where an increase in entropy, a mess, a disruption, a breakdown of order ultimately created space for a new form of order? Or a new opportunity? Maybe a chaotic move to a new city led to a better job. Or the dissolution of an old routine made way for a healthier habit. The collapse of a star forged the elements for planets. In your life, the spreading out of one thing often makes room for something else to coalesce. What form has that taken for you? From that smooth start, that almost featureless beginning, you get this universe of breathtaking diversity. The whole cosmic story, from the first quantum fluctuation to the dance of a living cell, it's one narrative. It's the story of entropy increasing. That initial order that wound up spring, it set everything in motion. Gravity found its foothold in the tiniest ripples. It sculpted vast clouds into galaxies. It ignited the nuclear furnaces of stars, and those stars became the first great engines of dissipation. They traded gravitational order for radiant disorder. And in that process, they forged the elements of chemistry and planets. On at least one world, bathed in a constant flow of stellar energy, matter organized itself. It formed self-sustaining patterns. Life emerged as another form of entropy export, a whirlpool of chemistry that builds local complexity by sending waste and heat back out. And from that biological complexity came minds capable of wonder, minds asking the questions that trace this arc back to its source. So the key is this. Complexity isn't a rebellion against the second law. It's the law's most magnificent consequence. The universe is a creative engine. It transforms its initial, improbable order into a dazzling diversity of structures. It does this through the process of dissipation. Every galaxy, every leaf, every thought is a temporary eddy in the universal flow toward equilibrium. It's a beautiful, transient shape the river of decay takes on its journey. The astronomer Rebecca Elson captured it. She said, "We are the universe contemplating itself. In our curiosity, in our science, in our art, the cosmos has grown an eye. An eye to look back on its own origins, on its own fate. See chaos not as a meaningless end, but as the necessary beginning. The beginning from which all structure and sensation arise." The night sky isn't a static picture. It's a story in progress, a beautiful, inevitable unfolding from simplicity to richness, all of it driven by the fundamental tendency toward disorder.